Hello, everyone, and welcome to the Big Data Conference, the 2021 edition. My name is Manuel Middelburg, and I'm going to be your moderator today. Today, I have the great pleasure to introduce a topic that is going to be very interesting for everyone who's ever been in the Kafka domain. It is my great pleasure to introduce today Carlos Manuel Duclos-Vergara, who's been a regular presenter at this company and is the technology lead at Schibsted, and he's presenting today, as he just told me, from a very small town in Norway. Today, Carlos is going to give us a presentation on choosing the right level of abstraction for your Kafka projects. He's going to show us how you can use and develop Kafka applications using Java virtual machine languages so that you can choose between different levels of abstraction. Personally, I'm looking very much forward towards this presentation, and I'm pretty sure he's going to give us some great insights. I would like to welcome Carlos to the stage. If you have any questions during today's presentation, please use the Q&A option, which is provided on the screen in front of you. I will be monitoring the chat and the Q&A, but towards the end of the session, we're going to get started on moderating the questions. Thank you so much, and give a warm welcome to Carlos.
Hello, everybody. My name is Carlos Manuel Vergara, and I work as a technology lead at the Schibsted distribution. Today, we're going to talk about choosing the right abstraction level for your Kafka project. I am originally from Chile, where I grew up and went to university. I have lived in several countries, among them Belgium, the US, and Norway, where I've been living the past 15 years. I started with computers when I was about 10 years old, programming an old Atari Basic on a computer I got from my parents. And since then, I have never stopped. I currently work in Schibsted distribution, where we manage the distribution of newspapers and packages all over Norway. Before this role, I worked at the Data Foundations division, where we processed events coming from our trackers in our websites and mobile applications. The ingestion volume is about 1 to 2 billion events per day, while we output somewhere between 8 to 10 billions of events to other systems. The core of the Data Foundations stack is based on Kafka. Schibsted, for those who don't know it, is the leader media house in the Nordics. We're also the leading marketplace in the Nordic. Our brands Finn, Blocket, Oikotie, and now eBay, through our daughter through our daughter company Adavinta, are the leading marketplaces in the Nordics and sometimes even in the world. In addition, we are the owners of many other types of businesses, such as Lendo, Prisjakt, and others. Before we start, I just want to mention this. We are hiring. If you like what I am saying and want to work with these technologies, contact me after the presentation. My link profile is on my speaker page. So, that being said, let's get into it. We're going to talk about choosing the right abstraction level, so it seems natural to start by asking the question of what is an abstraction? An abstraction is a simplification of reality. It is a model that helps us understand the key concepts of a process or situation. A good abstraction contains enough information to represent the problem at hand without requiring extension. A bad abstraction requires extensions and extra information to model the problem. And sometimes a bad abstraction contains too much information, so we lose sight of the problem. For example, what do we see here? This represents many things. It seems to represent some kind of a stream where objects, or boxes if you want, have an expected path. There is a current path that we're seeing, and some kind of deviation, if you want to think it like that. We will now look at two examples, one of a good abstraction and one of a Bad abstraction. Keep in mind that a good or bad abstraction is based on the problem at hand, and that an abstraction can be good to represent one problem and bad for representing another problem. This is a good abstraction. It provides enough information to convey that this is some kind of vehicle without imposing unnecessary restrictions or providing too many details. We see that, yeah, there seems to be some kind of wheels, maybe some windows, but the important thing is that it doesn't matter if this is not a sedan or SUV or a sports car or a pickup. We just notice that there is some kind of vehicle. This, on the other hand, it is a bad abstraction to represent the problem because it provides too many details. We're soon going to start considering, like, oh, why is that color? The windshield is divided in two, and the windshield wipers seem to be in the way of the driver. Instead of focusing on the problem that it's delivering something, we start focusing on the abstraction itself. So this is kind of taking us out of what we are trying to do. Now that we have introduced abstractions, let's introduce Kafka. For those of you who don't know about Kafka, Kafka is a collection of distributed logs of immutable records. It is distributed because it divides the load among several collaborators. It is a log because it is an ordered sequence. And it's immutable records because once they are written, they cannot be modified. Let's get into more details. Data in Kafka is stored in logs, which are called topics. For performance and reliability reasons, a topic can be divided into partitions. Data is written and read in records, and each record is written to one partition. Partitions can and should be replicated. Records, as I said, are written to partitions in a topic. It is the producer of the record that decides to which partition the record should be written. The default algorithm to decide the partition is very simple. You take the key of the record, you hash it, and then you apply modulo the number of partitions. This makes sure that the partitions are going to be allocated more or less uniformly. This algorithm can be changed if needed. The records are written to what is called the partition leader. Once the record is written to the leader will notify followers so they can synchronize to the latest state. Now, at the other end of the application, we have consumers. And records are consumed by what is called consumer groups. A consumer group is a group of one or more consumers that divide a topic among themselves and process the records. Each topic can be consumed by many consumer groups, and they are all independent of each other. A consumer in a consumer group is assigned one or more partitions, depending on the number of consumers and partitions on a topic. If there are more consumers than partitions, some consumers will not be allocated partitions and will remain standby. Now, I've been using the term consumption, but what does it mean to consume a record? In Kafka, records remain in the log after they have been read. This is opposed to, for example, a queue, where we take the record out of the queue for processing. The way Kafka does it allows several consumers to consume the record over time instead of letting just the first one to get to the record to consume it. At some point in time, and depending on the strategy, records will expire. This means they will be deleted from the log. And in Kafka, there are two main expiration strategies. Time-based, basically we say that records will expire after a certain period of time, and there is the compaction. we say that records will be compact and we will keep just the last value for a given key. That way, we avoid the log to grow exponentially when we are writing records, but we still keep only the values that we are interested in. So now that we have seen a little bit of the basics of Kafka, let's look into the low-level API, what it's called the Kafka Consumer and Kafka Producer API. The low-level API is role-based. This means the API mirrors the behavior of the three available roles. We have consumers, we have producers, and we have admins. Let's start with the producer role. The producer role is the role that writes records to Kafka. Kafka producers can be shared among threads. The producer has three modes of operation. We can have what it's called simple mode or the happy-go-lucky mode, which is the fastest mode, but it doesn't protect against duplicates. We can have it in the idempotent mode, which avoids duplicates by taking control over retries. This mode guarantees exactly one semantics, but only in the current session. This means from the moment the consumer is started to the consumer stops. In case of problems, it requires the producer to be shut down and some manual intervention. Finally, we have the transactional mode, which requires collaboration from consumers, because the producer and the consumer have to agree on consuming only committed transactions. But it guarantees exactly once delivery semantics and no duplicates. The next role is the consumer role. This is the role that reads records from Kafka. Consumers cannot be shared across threads. Consumers work in consumer groups. A consumer group is a group of consumers that read records from the same topic in a coordinated fashion. There can be many consumer groups reading from the same topic, and they are all independent from each other. Now, in a consumer group, there will be several consumers, but each consumer will be allocated one partition or several partitions, and it will be exclusivity. There cannot be two consumers in the same consumer group consuming from the same partition. Finally, we have the third role, which is called the admin API. And the admin API focuses on operations to manage topics in the Kafka cluster. The admin role is used to manage and create, delete, and modify topics. It is very seldom that one requires the admin API, but it's good to know that it exists, because sometimes we will need to create topics manually or have a way to modify them and all that. It's also worth mentioning that it is possible to separate permissions so that some clients will only be allowed to connect as consumers, some only as producers, and some only as admins. But we will not look into that in this presentation. Now, we have talked about the low-level API. Let's talk about what it's called the Kafka Streams API. Kafka Streams, it's an API that it's based on high-level operations. And it's not based on what you're doing with the data. It's not role-based as the low-level API. This is about what you want to do with the data. And when I say Kafka Streams API, well, there are actually two APIs that you can choose from. Most people will use the DSL, the domain-specific language API, because it's a nice and simple and yet very powerful API based on a specialized language that allows you to build complex pipelines. There is another API in the Kafka Streams side, which is called the Processor API. And this is a low-level API that it's based on the notion of a graph and processors. The DSL API is implemented on top of the Processor API. Now, that means that the operations that you find in the DSL API are all implemented using those processors. And then what we get, we can build new operations that are not supported by DSL if we want to use the Processor API. We will look into this a little bit later. Another thing that it's worth mentioning is that Kafka Streams operates only on data that it's already present in the Kafka cluster. Now, DSL operations allow data processing without thinking about the details underneath. The DSL spares you for the nitty-gritty details. You just focus on what you want to do with the data. And a typical pipeline includes operations such as fluff map, which means you take one event, one record, and you might produce 0, 1, or multiple records. Maps, where you take one record and convert it to something else. You can have filters. Basically, you just only some of the records that match the criteria will pass the filter. You can have window operations, either time windows or other types of windows, where you will be able to say, like, okay, I want to perform these operations only in this subset of records. You can have joins. You can join two different topics and do something with them. You can also do the opposite, which is branching. You can say, like, okay, now I'm going to send all the red balls to the left and all the blue balls to the right. The aim of this API is to simplify the building of complex pipelines using standard operations. Once one or more sources are added, we can easily process the records. The API will take care of building the underlying infrastructure for us. Let's look at an example. Here we have a very simple example of Kafka Streams. We have a function. This method will create a word count stream. The first thing that we need to do is to create a stream. And we start from an input topic. And then we'll skip the pattern there. I'll come back to it. Then what we do is we take the stream that we get in the beginning, the text lines, and we will do a flat map. And what I'm going to do is we take the value that we are reading, which might be a line from a file, for example, and then we will split it into an array. Basically, we will separate the words. As you see there, our regex there will separate words. And then we will lower it. We will make it lowercase. Then we will group them. And the group by takes both the key and the value and outputs something, the grouping that you want to do. In our case, we just ignore the key because we don't care about the key, but we take the word. So we group everything by each word that we are seeing. And finally, we count them. So what we are doing here is basically take a line, split it into an array. For each element, separate the word, then group them and count how many of those we get. The final step is to take that table that we are seeing there, convert it into a stream, and then write it to a topic. So we'll have an input topic where we get what we're reading, and we will produce an output topic. And as you see, the output topic in the final line there, it says produce with. It will have a string as a key, basically the word that we're interested in, and it will have a long as a value, basically how many times we are seeing that word. Now, let's look at the processor API. The processor API is still a high-level API, but it offers a lower level of abstraction than the DSL API. The processor API allows us to perform operations that might not be defined in the DSL. The processor API, it is based on the idea of creating a graph of processors, hence the name, and then connecting them. Once we have built our graph, the API will take care of building the underlying infrastructure for us. Here is, for example, a simple network graph of processors. The graph of processor is constructed based on the operations that are required. Records can be transformed, filtered, and forwarded, or stored based on the graph configuration. Here you see that we start with records, which comes from the topic, and then they are applied, for example, in the processor 0, we branch. Either we send them to processor 1, or we send them to processor 2. When we get to processor 2, we write them to async. Basically, we create a topic that it's an output topic. And in some occasions, we might send events to processor 1. That's why the dotted line is there. From processor 1, we will apply some kind of transformation. We don't know what. It doesn't matter for this example. And we get to processor 3, where we again will create another sync. We will write this to another topic, to another output topic. Now, wait a second. Both Kafka Streams API seem all fine and dandy. But there is the question of, why do I need this API if I could do all this manually by having a producer, a consumer, and, for example, Java 8 stream operations or Scala operations? Many programming languages and frameworks offer this kind of functionality. Well, there is a big difference, and in fact, there are several key differences. The first one is Kafka Streams will internally create backing topics for the operations, so that if a node crashes, the results of the operations can be taken over by a new node without data loss. This is opposed to, for example, implementing this with a consumer, Java 8 stream operations, and then a producer. If our application crashes there, then we have to restart everything, and we don't know exactly where did we start without going inside and start looking at things. It's possible to do, but it's more work. Kafka Streams will only keep data in memory for as long as it's needed. And to accomplish this, it uses RocksDB internally to organize data. Data that it's not needed or that needs to be persisted is written to a Kafka cluster. This means that the application uses less memory because only the required data is in memory. This is opposed to, for example, to continue with the Java 8 streams example. If we start doing a streams operation and do many transformations and all that, that's memory that it's happening locally in our machine or in the machine where we are running. So if, for example, we are performing a grouping or some kind of aggregation or that kind of operations, all that is local in our machine. If we want to save the state, we need to manually implement this. By using Kafka Streams, on the other hand, this will happen automatically. We don't need to worry about that. Kafka Streams is smart enough to realize like, oh, you have an aggregation, I will save the state. And that we don't need to do anything. It will save the state for us and make sure that if we crash, the next one in line can continue from where we left. But not everything is as good as one might think. There are some downsides too. One of them is Kafka Streams needs to use the same number of partitions all over the place. This means that if your input topic has, for example, 40 partitions, then you have to keep using 40 partitions. Or you will have to repartition the topic, the input topic, to a topic with fewer partitions. The reason for this is that Kafka Streams, when creating the topology, the connected graph, we will have to make sure that there are enough consumers and producers on both sides. So if we don't have the same number of partitions, then it's very difficult to actually, for Kafka Streams, to know exactly how do I divide the load. Another downside is that data has to be already stored in the Kafka cluster. Now, it is technically possible to read data. You can use Kafka Streams, for example, for a read a file, create your own processor node that reads a file and uploads it to the Kafka cluster. That is possible. But Kafka Stream is based on the notion that you will already have the data there. So you probably have a producer application somewhere that it's doing that for you. And your only concern is take the data from the Kafka cluster and process it. And finally, performance of Kafka Streams applications degrades very quickly when you interact with external systems. What do I mean by this? For example, if you need to perform a REST query, for each record that you get, you need to perform a REST query. That stops the stream processing in a way. You have to wait for the stream, for this REST operation to function. One way to do this, for example, will be to create a processor node that creates all the queries that you need and waits for the answers and then do a join. But if you just do it in the middle of the processing without thinking too much over it, then you will pay a big performance price. Now, let's now talk about how to choose the right API for your project. And we need to come back to this where we started. Remember the short discussion about abstractions. We have a look at the different APIs, and the different APIs target different use cases and are, of course, designed to satisfy different requirements. So the first thing that we need to do is to talk about your application and the goals that it has. What are you trying to achieve? And let's look at and talk about some common scenarios. I want to start with this scenario because this is probably the most common scenario for most people. You have data and you need to process large amounts of data. So this is a continuous stream of data that needs to be processed. Each record has to be processed and possibly enriched with data from other systems. Data has already been written and made available in the Kafka cluster. For example, you have a REST API that just takes whatever comes, validates that the format is right, and pushes it into a Kafka cluster using a Kafka producer. What do you do in this case? Well, this is a typical, almost textbook situation where using Kafka Streams is the right answer. Because Kafka Streams provides the high-level operations that can be applied to data and takes care of creating the backend infrastructure. If the DSL API is not enough, then the processor API can be used to create new high-level operations. What I was explaining a little while back. For example, let's say that you need to enrich data with data from another systems. Maybe you need to create a processor node that will fetch the data and create a stream somewhere so you can join the two streams and avoid having this stop and pause in the middle of the stream processing. Maybe you need to perform a special kind of mapping that it's not represented by either a flat map or a map. Or maybe you need some kind of a special filter, or I don't know. There are many operations that sometimes you don't think that might appear, and they are difficult to implement. Let's look at another very common case that you will find. The pub/sub paradigm. This is a very, very common programming pattern in distributed systems. Basically, you have systems that are producers of events called the publishers, and you have systems that are consumers of those events, which are called the subscribers. The publisher doesn't know about the subscribers, and the publisher publishes events regardless of if there are subscribers or not. Publishers publish to their own topics. Systems that are subscribers can subscribe to the topics that they are interested in. This is a classical situation where the low-level API is the best way to go, since the producer-consumer API is a one-to-one mapping for this situation. Basically, the publisher produces, the subscriber consumes. Another very common case is when you have a chain of processes and one stage is slower than the other. Let's say that in your processing of data, you have one step that might require some processing that is very, very slow. So you need to decouple the systems so that each system can work at full speed. And slower systems do not limit the performance of the other systems. The Kafka consumer, Kafka producer API can offer a lot because it allows us to control the situation and decide ourselves how we want to implement this, as opposed to Kafka streams, in which we don't have that much control because the backend infrastructure will be created by the library itself. One typical way to solve this is, for example, fast systems can consume events from topics with few partitions and write the output to topics with a high number of partitions. So they can be consumed by slower systems. Let me show you an example here. We have two partitions and we have two fast nodes. I just wrote node because I didn't have a better name. So these two fast nodes consume only from two partitions because they can't keep up with the load. And then they spread the load across several partitions. There is one slow node that consumes from each partition. That way, we can process a lot of events in parallel without having to wait for one operation to finish before we can start the next one. The slow node can either write to one partition or several partitions, and we can kind of tune the system to be able to adjust the speed according to what we need. Now, there is one big word of caution here, because this strategy has to be used very carefully. The reason is these might alter the ordering of events. Many systems do not care about the ordering of events, but for some systems, it's very important that the events are in the right order. And here we have two situations. There is an absolute ordering and there is a relative order. An absolute order is that events, regardless of where they come from, they have to happen in a particular sequence. Otherwise, the outcome of the system will be different. Relative ordering is that not all events have to happen in a given sequence. It's only some events, basically the ones belonging to the same key. All those events with the same key have to happen in the right order. So as long as we are sure that our system doesn't require absolute ordering, and as long as we guarantee that events will be allocated to the same partition and will follow the same path for the same key, then we can use this strategy to tune the system to handle both fast and slow nodes. And finally, I have the final and usually very generic situation. You need to share data among different systems. This is also a very common case. You have many different systems that need to share data with each other, and you need a data bus. In this case, there are systems that produce data and some systems that consume that data. Consumers usually process the data and send it back to the bus for consumption by other systems. This case is a mixture of the previous cases, because some systems are pure producers of data, while others are pure consumers of data. For those systems, the producer-consumer API is perfect. There are other systems that process data and send it back to the bus. For those systems, the Kafka Streams API is the best option. So in this case, you have to mix and match. You have to divide this into the different processes and stages of your pipeline and create different applications using the right API. As I said, if you need to produce data, for example, by reading from a database or by reading from files, or by receiving events via REST API, you create a producer application on one side. If you need to write processed records to a database, for example, you create a consumer database that consumes from a given topic. And in the middle, if you need to process those data, process those records and transform them and do all that, you use Kafka Streams to do that processing. You might even need to implement something in between, but Kafka Streams should do most of the transformations that you need. And with that, I hope you really have enjoyed this presentation. Tomorrow, I will have a workshop where we will look at the performance of Kafka applications and all the nitty-gritty details about what I just talked about. So I hope you join me. And now I'm ready for questions.
Good. Thank you so much, Carlos, for this wonderful presentation. I definitely learned a lot, and I thought it was a very good overview of some of those major aspects and the differences in APIs. For everyone who is on the call, in case you would like to ask any kinds of questions, please type them into the Q&A box, and we will be happy to moderate them. While you take the time to do that, Carlos, I already have a couple of questions for you, which I hope you can shed your light upon. One of the questions is how does Kafka high variability? So suppose spikes in loads, and how does the system scale up resources or scale it down? So is there any difference there in between the DSL and the processor API?
Okay, so the question is about how to deal with peaks in load.
Yeah, correct.
And
yeah,
there is no one answer, that there is no one size fits all. It all depends on the occasion. But let's start by looking at how Kafka Streams actually assigns workers. So Kafka Streams will internally create threads, worker threads, to process the data. And Kafka Streams is based on top of the low-level API, which is based on the Kafka consumer and Kafka producer. So what Kafka Stream does is to create Kafka consumers and join and create a one big consumer group. Now, A consumer group at some point has enough workers, consumers, for all the partitions. And once you have reached the one-to-one mapping, you cannot add more resources. So if you have a lot of load, but you only have a few partitions, no matter what you do, basically you cannot consume more because you're limited by the number of partitions. So in the case of Kafka, this is a situation of where you have to plan ahead from that point of view, purely from the topic point of view, on what is your average case and what is your worst case scenario, and pick a value that will satisfy somewhere in between. If you just pick, for example, in my previous position, we have this situation very, very often, because at 7 o'clock every day in the morning, people will open their mobile devices and will start reading news. And at that point, we have a big peak of traffic that will last at about 9 o'clock in the morning. So we had chosen a number of partitions that allowed us to distribute the load so we could scale the workers. But when we didn't need it, we had that number of partitions was low enough that we could scale down and still have enough workers, even though they might be processing 3 partitions each, but we had enough workers to do that.
Good. So if I can summarize, one of the key things is you would need to, in advance, consider your peak loads, and as you mentioned, what is your worst case scenario? Is that correct?
Yes, because this is intrinsic to Kafka. You cannot consume more than the number of partitions.
Good.
So if your number of partitions is too low, you're going to be limited by that.
Good. Thanks so much. I see some other questions coming in, so I hope we still have some time to moderate a couple. One of the questions that came in is, does RabbitMQ include functionality that is similar to Kafka streams, or is Kafka better in this area?
Well, I'm not terribly familiar with RabbitMQ, but RabbitMQ is the equivalent of Kafka. Kafka Streams is a library that it's built. It's a framework, and in that sense, it's more similar to Flink, to Apache Spark streaming, that kind of side. It's based on the processing more than on the processing of things. So if you have a framework on top of RabbitMQ, that framework it's comparable to Kafka Streams. RabbitMQ can be compared to Kafka, and there are comparisons all over the internet about which one you should choose.
Good. I think that's a very good question. And I have another very interesting question. I think we just have time for one more. And that is, can you switch between implementations easily? So suppose that you have implemented your solutions using the DSL API. Is it then easy to switch towards a processor API, or does that require a completely different setup and structure?
Yeah, that's a very good question, and it's a question that requires some kind of side explanation, because the DSL API, as I mentioned, it's focused on the operations. So basically, you don't know what's going on, and I'm going to go into the details of this tomorrow in the workshop, but you know that you get data in, you process it, and you get data out. Now, the processor API, it's also the same, but except that the process itself, it's implemented by you. And that means that you will have to kind of pipe different things together. Now, if you just start from the code, the DSL, it's very different from the processor API. So they're not very, you cannot just apply some kind of magic transformation and you will get the processor API. Good. But if you know what the transformation is, it's not that difficult to implement the transformation. You can find the source code for Kafka streams, and you will see that the transformations provided by Kafka streams are not that complicated.
Good. I think that's a very good answer, and I think I'll join your session tomorrow to find out a little bit more about that. Thank you, Carlos, so much for this very insightful presentation. Also, the questions. I would like to thank all of the participants for joining today. We are unfortunately out of time, and we're looking for the next sessions already. So I would like to take this opportunity to once again thank Carlos so much, and good luck with all of the other very interesting sessions in this conference. And Carlos, good luck tomorrow with your workshop. I'm very sure that that's going to be very interesting. Thanks everyone for joining today, and we're going to see each other later. Bye-bye.